This is our presentation for ECEN 361 at Brigham Young University, Idaho. It's an embedded systems project, and we made a balancing robot that we jokingly called Wally Prototype. And we are going to share with you a little bit about the build and components and some of the methods that we use to get our robot working, and then at the end we will show a demonstration of the robot working.
So what you're seeing now is an overview of the circuit design that we use to implement our balancing robot. The main thing that we wanted to focus on here is that we use the Arduino Pro Mini as our microcontroller. And we used the 5 volt, there's different versions, but we used the 5 volt version for that. And so you can see here we've got a 5 volt VREF coming in, and then we've also got a regulator over here that is supplying our 5 volt VCC power to our Arduino and the rest of our components. And so here we have our communication between the Arduino and the gyro. We used the MPU 6050 sensor for the gyro, and it's a gyro accelerometer combination, and it has channels in both the X, Y, and also the Z that can read simultaneously, so it gives us very accurate readings. And then from there we've got the drivers for our stepper motors, and yeah.
So one of the things that was necessary to implement in our code in order to make this robot work was something called a PID control system. The PID stands for well, there's the way a PID system works is that you have a desired output, and with your input you're trying to get ideally as quick as possible to your desired output, and sometimes you might overshoot it, as you can see in the graph, and sometimes you might not get to your desired output fast enough. And so there's a mathematical method that that can be used in response to your input so that you can get the desired output. So, and those three things are the PID, proportional response, an integral response, and a derivative response. And essentially the way that works, going down to the bottom graph here, is that we have an input. It goes through, in this case, it goes to our Arduino and gets readings from the gyroscope and accelerometer as to how the robot might be oriented. And then when it's off and it's not at its desired output of straight up and down, it sends that information back into the input so it can make the necessary adjustments to the controls of the motors so that we can get the robot to balance properly. And then we'll talk a little bit about the software timer interrupt system.
So the last thing, big thing that we needed to help control our stepper motors was a timer interrupt. Basic idea of a timer interrupt, it doesn't need an input signal. It you set an interval for when you want this interrupt to happen. And that is set in Arduino using these 5 registers, the TCRA, TCRB, TNCT, the OCRA, and the TIMSK. All these, when you set them, with the OCRA is the main one, and that's how you set the frequency in which the interrupt will occur. So the idea of having an interrupt is so that when we need to move our motors at a specific rate, they will overcome anything else that's happening in the program. So when we're trying to calculate steps, every 38 microseconds we'll go and run the motors to make sure that we are standing up straight. And so that's pretty much how we use this for our robot. So here's a quick little demonstration of how it worked.
So when we switch it on, there's going to be a time of calibration, and then after the calibration is done, the lights on the robot will go on. So now the gyroscope has gotten a number of good readings from from the accelerometer, and now it's ready to be set upright. And I'll try to do it in such a way that you can see that it balances pretty well. If it doesn't quite get a good reading, we might need to reset it and then stand it back up. And then we can get a fairly stable, and then it responds well to inputs as well, as you can see. It'll balance it out. We don't quite have all the kinks worked out of it.